Hello, I'm Elliott.
And I'm Wasef. Today we'll be showing the double slit experiment. This experiment shows that photons have characteristics of particles and waves.
This experiment may seem simple at first, but it begins to get more and more complicated.
Why don't we show them what we need for this spectacularly stupendous experiment?
Here's our laser. Its wavelength is 650 nanometers, or 0.00065 millimeters. This wavelength makes it shine red.
This is our business card. We have cut two slits for the laser to shine through, and having the two slits creates the diffraction pattern that you will see later on in the experiment.
Here is what will support our laser in our business card that has two slits in it. We put our laser right here.
And you put the business card right here. And you just shine it through the double slits. Good. Cool beans. Here's our experiment.
So, Wasef, what was the clip showing?
Well, that's a very simple question with a very complicated answer.
Well, let's get started. So, first, let's look how particles act.
Well, this picture shows how particles will react when shot through the two slits. Unlike waves, particles travel in a straight line. As they go through both slits, they create the shape of the slit they went through on the back wall. Now, Elliot, how about you explain to us how waves act in this experiment?
Well, this picture shows how the waves will react when shot through the two slits. Like particles, the waves go through the two slits. However, unlike particles, the waves diffract and interfere with each other, forming this pattern. The end result are all the possible outcomes for the wave to land on the wall.
Now that we know that, let's tell them how light acts.
Good idea. Let's start.
Well, light acts like both a particle and a wave, depending on the circumstances. So, Elliot, can you give an example of when light acts as a particle?
Light can act like a particle when it bounces off a mirror and back at you, or just in a solid stream so that you can see the image. Now, why don't you tell us when light acts like a wave?
Well, light acts like a wave when it goes through a small gap and spreads out as it goes throughout.
So, Wasef, those diagrams look a little familiar, don't they?
Yeah, you're right. This same method was used in the experiment we showed earlier. How about we take a look at the laser close up to see how they match?
Good idea. Let's do it.
Okay, so here's the laser that we showed in our experiment. You can see the parts where waves diffracted and spread across the wall.
And here's the diagram. As you see, the light and waves act as the same way when going through an opening. Now, Wasef, the viewers may be confused on how this is true. Let's show them the mathematics behind this.
Good idea. Let's go. First, how about you explain to them about the variables in the experiment?
Good idea. Now first, here's lambda. And here is our equation.
Wait. Take it one step at a time.
You know what? You're right.
Let's
These are
go.
middle schoolers. Let's go. Now first, here's lambda. These are the bright beams of light, otherwise known as fringes. They start out bright, but as they spread apart from the first one, they get dimmer and close together. X is the difference between the central fringe and the next fringe that you measure. N is the order of fringes that you measure. So, if N were equal to 2, then you measure 0 to 2.
D is the distance between the two slits that we put in the business card. In our experiment, the distance between the slits was 1.5 millimeters. L is the length from the slits to the viewing surface area. In our experiment, that distance was 5,550 millimeters.
This is our equation. Lambda equals dx over nL. In our equation, lambda with a wavelength is 650 nanometers, but we must change it to millimeters, and that is 0.00065 millimeters.
That's all you're going to do? In our equation, D, or the distance between the slits is equal to 1.5 millimeters. Also in our equation, x, or the distance between the fringes, is what we are solving for, so we don't know that part yet.
In our experiment, n, or the order of fringes, is equal to 1. So we measure between the middle and the first fringe. Since it is equal to 1, we don't have to keep it. Okay, finally, L, or the distance between the slits in the viewing circle, is equal to 5,550. Okay, now we have to solve for x. First step is to multiply 5,550 by both sides. Now that we have this, we must multiply 5,550 by 0.00065. Now we have 3.6.
Next, we divide 1.5 by both sides. And 3.6 over 1.5 is equal to 2.4. So x equals 2.4, and 2.4 is equal to x, which means that there should be 2.4 millimeters between every fringe on the laser in our experiment, according to this equation.
So, Wasef, who was the man who invented this experiment?
Well, my dear Elliott, it was invented by a man named Thomas Young. How about we tell the audience more about his history?
Sounds like a good idea.
Well, in 1801, Thomas Young was able to offer some very strong evidence to support the wave model of light. He placed a screen that had two slits cut into it in front of a single color of light. Do you remember the results of Thomas Young's experiment?
Well, just like in our experiment, which is a replication of his, he found that light acts as waves when going to an opening and acts as a particle when out in the open. How about we take a look at Thomas Young? Well, Wasef, this has been a very productive project, I'd say.
Yeah, but it took us a long time.
Well, Wasef, we've learned a lot, and I guess it's time to reflect.
That's a good idea.